In this video, we will be talking about what is, in my opinion, one of the deepest results in optimization, namely the equivalence between optimization and separation. Our point of departure is the fundamental theorem of integer programming, Meyer's theorem. We have seen that solving an integer programming problem is equivalent to solving a linear programming problem over the integer hull of the polyhedron. However, this linear programming problem potentially has a very large number of constraints. In fact, they can be exponential with respect to the original description. And on top of that, even the original description of the integer programming problem can have an exponential number of constraints, as we've seen, for example, in the traveling salesman problem. And these two examples highlight how often we're dealing with linear programming problems with an exponential number of constraints. In the first case, we're talking about the linear programming problem over the integer hull of the polyhedron, and in the second case, we're just talking about the standard linear programming relaxation of our integer program. So the first goal of this video is to understand how we can solve efficiently linear programming problems with an exponential number of inequalities. If we want to do so, clearly we cannot generate explicitly all the constraints, because just doing that can take exponential time. So how can we solve efficiently, or in polynomial time, such linear programming problems? In the past lectures, we've already discussed, in fact, an idea on how to do so. In some cases, we can solve the separation problem efficiently, so without generating explicitly all the constraints, and we have seen that, for example, for subtool elimination inequalities. And the question is, how can we use it? We discussed how to use it in a cutting plane algorithm, but of course that's not enough. This doesn't give us any guarantee on the running time of the cutting plane algorithm. So the idea is still to use the separation problem, and we will see that this will not be a cutting plane method. Our first main result in this section is that if we can solve the separation problem in polynomial time, then we can solve in polynomial time also the optimization problem. So let us formalize once and for all exactly what are these two problems. In the separation problem, we're given a polyhedron and a point x bar in the same space. And we need to either show that x bar is in the polyhedron, or if not, we need to give a valid inequality for p which is violated by such point. On the other hand, in the optimization problem, we're also given a polyhedron, but now we're given not a point, but an objective function. Now we need to do one of the following three things. Either find a point in P that is an optimal solution to max Cx for x in P, or we need to show that P is empty, or we need to find a direction z for which Cz is unbounded. In order to prove this result, we will be using the ellipsoid method, and now we're going to give an outline of this algorithm. So essentially, all the main idea of the ellipsoid algorithm is contained in this slide. So let's first discuss our input and output. In input, we have a separation algorithm for a given polytope P. And in output, we need to give a point in P or a proof that P is not full dimensional. Now at this point it's unclear why this is our output, because that's not exactly what we're interested in. But we will see that essentially if we're able to obtain this output in polynomial time, then we can actually solve the optimization problem. We just need a couple more steps. So for now, let's focus on this input and this output. So in the initialization step, the ellipsoid algorithm obtains a large integer t star, we will discuss this in more detail later, and an ellipsoid E0 that is guaranteed to contain P. Now the number t star will be our total number of iterations, and now we set a counter t to count exactly the number of iterations, and we set it to 0. Now the picture below represents a general iteration of the algorithm, and as you can see, think about this ET to be exactly your E0. We have an ellipsoid here that contains your original polyhedron P. Then let's discuss a general iteration T. At the general iteration T, we will have already obtained an ellipsoid ET that still contains P. So at the beginning, of course, this ET is exactly our E0 in the initialization step. So the very first thing we do is pick the center of the ellipsoid ET, let's denote it by xt, and just check if it is in P. In this case, xt is the center of ET and it's not in P. If it is in P, though, we can stop, of course. Remember, in our output, we can just terminate with a point in P. So now assume that xt is not in P. In this case, since we have in input a separation algorithm for the polytope, we can find a constraint from the original system which is violated by xt. In the picture below, this is exactly this vertical inequality. In this case, as you can see, this is a facet defining inequality of P, but it doesn't have to be. It can be just any inequality valid for P and not valid for xt. Next, we find a new ellipsoid, ET plus 1, which contains ET intersected the new inequality. In the picture below, the new ellipsoid is this one on the left, and as you can see, it contains the old ellipsoid intersected the new inequality. Clearly, this new ellipsoid still contains our polyhedron P. And at this point, we're essentially done with our iteration. We increment T by 1. Then we have our stopping criterion. If T is strictly smaller than T star, you continue, we perform another iteration. Otherwise, if T is equal to T star, we stop with the statement that P is not full dimensional. So almost all this algorithm is extremely clear. So in a sense, it's always clear why it works, except for the very last line. What is definitely unclear at this point is why, when T is equal to T star, we can actually argue that P is not full dimensional. And we will discuss this in a bit. But first, let's state the main theorem regarding the ellipsoid algorithm. So we have that the ellipsoid algorithm terminates with the correct output if E0 and T star are chosen large enough. So this tells us that the algorithm is correct. Furthermore, this choice can be made so that the number of iterations is polynomial. So first, I want to discuss why the algorithm is correct and why the number of iterations is only polynomial. So we're not going to prove anything, but I just want to tell you the observations that allow you to prove this result. So the first observation is that the very first ellipsoid can be constructed with volume at most delta, where with volume at most a number delta, where the encoding size of this number delta is polynomial in n and in the size of the coefficients of the system describing the polyhedron. Next, it can be shown that the volume of the ellipsoid at every iteration decreases by a factor ρ, which is strictly smaller than 1 and depends only on the dimension n. Finally, it can be shown that there exists a positive epsilon, which is very small, but still with encoding size polynomial in n and in the size of the coefficients of AB, such that if P is full dimensional, then the volume of P is greater than or equal to epsilon. Once we know these three observations, which of course require a proof, we are able to understand why the number of iterations is polynomial and also why the algorithm is correct. In fact, at this point, the volume of the ellipsoid at iteration t is upper bounded by ρ to the t, the volume of the original ellipsoid, by just using these inequalities here. And then using this inequality, we're able to calculate how large t should be in order for the volume of ET to become smaller than this epsilon. And the t that you obtain is t star equal to the logarithm of delta over epsilon. At this point, if the ellipsoid algorithm arrives at iteration t star, the algorithm has constructed an ellipsoid E t star with volume smaller than epsilon, so it can conclude that P is not full dimensional. Therefore, first, the algorithm is correct, because the output is indeed correct, and the number of iterations is polynomial, because it's log delta over epsilon, and both delta and epsilon have encoding size polynomial in n and in the size of the coefficients of a and b. So at this point, is this enough to argue that the ellipsoid method runs in polynomial time? Well, no, because we've understood that we only need polynomially many iterations, but we still have to check that every iteration can be done in polynomial time. And in order to do that, we again have to make few observations. So the first question is, how do you construct in a general iteration the ellipsoid et plus 1 starting from et and the inequality obtained? The good news is that the ellipsoid et plus 1 can be computed in closed form. However, it cannot still be obtained in polynomial time because this formula involves square roots. But this can be fixed. So essentially, instead of picking exactly the smallest ellipsoid containing this intersection, we can construct an ellipsoid which is slightly larger, but the slightly larger ellipsoid can be obtained in polynomial time and there are no square roots involved. And these are all the details I want to give you about the ellipsoid algorithm. I don't want to enter into detail. And if you took the linear programming course with me, you've already seen more details regarding this algorithm. Now, instead, I want to focus on how you can use the ellipsoid algorithm to solve the linear programming feasibility problem. Remember, at this point, the ellipsoid algorithm only tells us that either the polyhedron is non-empty or it tells you that it's not full dimensional. And note that, by the way, if the input of the algorithm is a polytope that is not full dimensional, then the output could be either, it could give you either a point in such a polyhedron, even if it's not full dimensional, or it can tell you that it's not full dimensional. So now, how can we solve the feasibility problem by using this algorithm that we've just seen? Well, of course, if the ellipsoid algorithm returns a point, then you're done. The problem is feasible. On the other hand, if the ellipsoid algorithm tells you that P is not full dimensional, then it's possible to determine a hyperplane which contains P in polynomial time. At this point, this hyperplane allows you to reduce the dimension of the problem by 1, and so you can just iterate. If you eventually arrive at dimension 0, of course you just have a point and you can easily check if this point is in the polyhedron or not. Therefore, this modification of the ellipsoid method outputs either a point in the polyhedron or a proof that P is empty. So we have solved our linear programming feasibility problem and we've done it in polynomial time. Of course, there are some details here to check, but the key fact is that here you're using the ellipsoid method at most n time, and so you still obtain a polynomial time algorithm. Great, so at this point we know how to solve the linear programming feasibility problem. So how can we solve instead our true target, which is the LP optimization problem? And this can be done, again, by using the previous algorithm, so the feasibility algorithm, on top of binary search on the objective value. Namely, we can obtain in polynomial time lower and upper bounds L and U on the optimal value of the linear programming problems. And at this point, we solve a feasibility problem over the better half of the objective function. So namely, we take our polyhedron P and require the objective function to be between U and the midpoint between L and U, which is L plus U half. If this problem is feasible, then we have already found a point in the polyhedron in the better half of the objective functions. So we will never care about the worst half of objective functions, namely the points with objective function between L and L plus U half. So we can update the bounds to the better half that we just considered and iterate. On the other hand, if this problem is infeasible, then it means that there's no point in the polyhedron that has an objective function in this interval, but there still could be a point in the worst half that we haven't considered in this problem. So we update the bounds to L plus U half, so to the worst half of the objective values. In both cases, as you can see, the length of the interval has been halved. In both cases, then you iterate, and it can be shown that after polynomially many iterations, you will end up with an optimal solution to the original LP optimization problem. So now that we know how the ellipsoid algorithm works, we can get back to our traveling salesman problem in an undirected graph. We have seen that the separation problem for the subtour elimination polytope can be solved in polynomial time. Therefore, applying the ellipsoid algorithm, we can optimize over the subtour elimination polytope in polynomial time, even though the number of inequalities is exponential. So we have seen the sketch of the arguments that allow you to show that polynomial separation implies polynomial optimization. The next step that we want to discuss is that actually also the reverse implication holds. So we will see that polynomial optimization implies polynomial separation. Therefore, we're saying that these two problems are equivalent. Let's state this result in a very imprecise way, and we will make it more precise later on. The separation problem is solvable in polynomial time if and only if the optimization problem is. And even more informally, this means that solving a linear programming problem is just as hard as finding a constraint cutting off a given point or deciding that this given point is in the polyhedron. In order to prove this theorem, we will definitely use the ellipsoid algorithm. Well, that's clear because we've seen that this implication holds exactly using the ellipsoid algorithm, but it turns out that also to show that reverse implication, we need to use the ellipsoid algorithm. On top of that, we need a concept that we have never discussed before, which is polarity. So let me state what is the polar of a given polyhedron P. So the polar of P, which we're going to denote by P star, is the set of pi's in the same dimension as P, for which the inequality pi x less than or equal to 1 is valid for the polyhedron. So essentially, it is the set of left-hand sides of inequalities that are valid for P whenever they are scaled to have a right-hand side equal to 1. So this definition can be confusing at first, so I think it's important to look at an example. So here we have a polyhedron P in blue, which is the convex hull of plus minus 1, 0, and 0 plus minus 1. So it's a cross polytope in dimension 2. So what is its polar? Well, it's not so simple to understand because we have to understand all the inequalities that are valid for this set, but definitely we can easily check that some points are in the polar. For example, let's look at the facet defining inequalities defining P. We have x1 plus x2 less than or equal to 1, and this inequality has a left-hand pi which is 1, 1. Therefore, the point 1, 1, which is this guy, is in the polar. Similarly, we have the inequality minus x1 minus x2 less than or equal to 1. So this gives us the point pi equal to minus 1 minus 1, and we obtain this point here in our polar. Similarly, with the other two facet defining inequality, you will obtain this point here and this point here. And it's a very good exercise at this point to check that indeed P star is just a convex hull of these 4 points. What is very interesting is that actually if you take P to be the red polyhedron here, then its polar P star is the blue polytope here. Just to see an example of that, a facet defining inequality for P is x1 less than or equal to 1. Therefore, the left hand is 1, 0, and we obtain the point 1, 0. Similarly, this is x2 less than or equal to 1, and we have the point 0, 1. And so on and so forth. You can also check that this is indeed the case, that the polar of the red is the blue. In fact, this is no coincidence, and we can state the following result that we're gonna use in our proof. If we have a polyhedron P containing the origin in its interior, so not on the boundary, then the polar of the polar is the original polyhedron. And in fact, in our example, we had that the origin was contained in the interior of our polytope. At this point, we're ready to prove the equivalence between optimization and separation. I will give just a sketch of the proof, which is quite appropriate since even the statement of this theorem is quite imprecise. This is a sketch of the proof. essentially I will give all the steps that are needed to prove this theorem, but without really looking at all the details. In particular, we assume that P is full dimensional and bounded. So these are assumptions just to make our proof simpler. We have to prove an if and only if, and one of the two directions we've already essentially shown. So let me write it here. So the first one is a polynomial separation, which I write in short like that. So polynomial separation over the polyhedron P implies a polynomial optimization over the same polyhedron P. And this follows from the ellipsoid algorithm. Therefore, we now focus on the opposite direction. So we need to show that polynomial optimization over P implies polynomial separation over the same P. Now, the first thing we want to do is essentially translate our polytope P so that it contains the origin in the interior, so that we can use the fact that the polar of the polytope is the polytope itself, and we're going to use that later on. So, first claim, x bar in the interior of P can be found in polynomial time. Once we found this point, then we can always replace P with P minus x bar and obtain that the origin is in the interior of P. So how can we show claim 1? Well, we only need to find n affinely independent points in P. Let me write it. We only need to find affinely independent vectors x0 until xn in P, because then x bar equal to 1 over n plus 1 sum for I then goes to 0 from n of xi is in the interior of P. Great, so how can we find these vectors? Well, the first one is obtained by just maximizing any objective function over P. Find x0 by maximizing any objective function over P. And now recursively assume that affinely independent vectors x0 until, let's say, xi have been found. Then you just need to do the same, so optimize a linear function over P, and you just need to choose this linear function so that the objective vector is orthogonal to the affine null of the current point. Choose C orthogonal to the affine null of x0 until xi. Solve max cx and min cx over P. At least one of these two problems will give you an optimal solution which is affinely independent from the previous one. and you just need to repeat until I equal to n. So this is the sketch of how you can prove claim 1. So let's apply, as we already said, let's translate our polytope. Now we're going to state and prove a second claim, which is very similar to what we want to show, but actually it's not. So claim 2 says that if you can solve in polynomial time optimization over p, well, which is exactly what we have as an assumption, then you can solve in polynomial time the separation problem. So we would like to show over the same polyhedron p, but instead for now we prove it over the polar p star of p. So what is actually this problem separation over p star? What does it mean? Let me write it down, because when we talk about the polar, things are always a little bit confusing, because essentially the variables in the polar correspond to the coefficient vectors in the primal. So the separation problem over p star is the following. We're given a point in the space, in the polar space, so that's let's call it pi star in Rn, and the question is either show that pi star is in p star, so this is clear enough, or give a valid inequality. So how does it look like? It will be pi, and the coefficient vector in the polar will be some specific x star less than or equal to 1 for p star, such that pi star x star is strictly larger than 1. So such that this linear inequality is violated by the point pi star. So how can we solve this separation problem over p star? Well, it turns out that everything you need to do is solve a linear programming problem over p. So given pi star in Rn, let x star be an optimal solution to max pi star x with x in p. Why are we interested in such an x star? Well, there are two cases, right? If pi star x star less than or equal to 1, then we're done, because this implies that pi star x less than or equal to 1 is indeed valid for p, which implies that pi star is in the polar. Let me write it. Then pi star x less than or equal to 1 is valid for p, hence pi star is in p star. Otherwise, we have that pi star x star strictly larger than 1, and what we want to show is that in this case the inequality pi x star less than or equal to 1 is valid for p star. If pi star x star larger than 1, we are also done, because we have that x star is in p, but it's also in p dual of the dual, which implies that pi x star less than or equal to 1 is valid for p star. So let me go back. Our task in this claim was to show either pi star and p star, which is exactly what we obtained in the first case, or to give a valid inequality pi x star less than or equal to 1 for p star with pi star x star larger than 1, which is exactly what we do here. We have pi star x star larger than 1, and the inequality pi x star less than or equal to 1 is valid for p star. Great, and now we are almost done. To finish this proof, we just need to use this claim together with the first part of the proof. So in claim 2, we have just shown that we can solve in polynomial time separation over p star. Now, at the very beginning of the proof, we've shown that the polynomial separation over a polytope, let's apply this to p star, implies polynomial optimization over the same polytope. So then we obtain that we can solve in polynomial time optimization over p star. Now, if we again apply claim 2 to p star, we have that polynomial optimization over p star implies polynomial separation over p star star, which is equal to p. Therefore, we will have shown that separation over p can be solved in polytime, which is exactly what we wanted to show. So let me write these two implications. So the first part of the proof. Applied to p star implies that we have a polynomial optimization over p star. And then claim 2 applied to p star implies that we can solve in polynomial time separation over p star star, which is equal to p. And that's the end of our proof. So let's get back to the slides. Now that we've shown the equivalence between optimization and separation, I want in the last 3 slides to give finally a precise statement of this theorem. In fact, we need P to be described in a reasonable way, and now we discuss what this means. In order to understand that, let's first consider the subtour elimination polytope of a complete graph with n nodes. Now the input to this problem could just be the positive integer n, because that's essentially everything you need to know to be able to construct the corresponding complete graph. But then in this case, it's clear that the theorem that we just shown, the equivalence of optimization and separation, cannot hold, because the encoding size of the input is essentially log n, but clearly we perform already n operation just to find a vector in the interior of P in the proof. Therefore, we're performing a number of operations that is exponential in the input size. So this example allows us to understand that we need to put some restrictions on how our polyhedron P is described in order for our theorem to be true. The definition that we will need is the following. A polyhedron P belongs to a well-described family if the following two conditions hold. First, if we denote by L the encoding size of the input needed to describe the polyhedron, then this number L must be at least as large as the dimension n. Secondly, there must exist a rational system describing our polyhedron where the encoding size of each entry is polynomially bounded by L. Once we've given this definition, we can finally give a precise statement of our equivalence result. So for well-described polyhedra, the separation problem is solvable in polynomial time if and only if the optimization problem is. I will not go into the details of why this definition is needed for this theorem, but you can immediately see that the first condition, that L must be greater than or equal to n, is needed because in the proof we perform a number of operations that is polynomial in n. Therefore, in this way, it's also polynomial in L. And the second assumption is needed because, for example, when the ellipsoid algorithm picks an inequality which is violated by the current center, then the size of this inequality will be polynomial in L. Finally, note that this second assumption does not ask for the whole matrix A and vector B to be of size polynomially bounded by L. It just asks that each entry is polynomially bounded by L, and this also implies that every inequality has size polynomially bounded by L. However, the number of inequalities doesn't need to be polynomially bounded by L. Finally, let's see some examples of well-described polyhedra. Well, the simplest example is when your polyhedron P is given by a system AX less than or equal to B, where A and B are rational and given in input. In this case, the encoding size needed to describe A is the sum of the logarithm of the entries, so it's definitely larger than n. And since the encoding size of A and B are polynomially bounded in the input, then so is each entry of A and B. So this really is a trivial example. The second example is where P is the convex hull of the integer points in a polyhedron defined by AX less than or equal to B, where the input consists of exactly A and B. In this case, we know that the number of inequalities defining P can be exponentially large in the input size, but still, this polyhedron can be shown that is well described. Another example consists of the subtour elimination polytope of a graph G if the input consists of the graph G itself. And this last example is not hard to see, so I think it's a very good exercise to try to figure it out. Finally, an example of a polyhedron that is not well described. This is the example that we saw immediately after our proof of the theorem. It is the subtour elimination polytope of a complete graph with n nodes if the input is just a positive integer n. In fact, this is the example that in a sense gave us the intuition to define well-described polyhedra. And so we should check that this polytope in fact is not well defined. And this is indeed the case because the input size is log n, which is clearly strictly smaller than n. So the first condition is already not satisfied. At this point, we have finally understood at least a formal statement of the equivalence between optimization and separation, and we've also seen a sketch of the proof. And this concludes our video on the equivalence of optimization and separation.